This is problem 82 of Neetcode 50 clone graph. So for this problem, we're going to use a React technique, which is a very good technique to answer interview questions. R stands for restate the questions. E stands for explanation. So go over an explanation, and then we're going to go to A. A means for basically what is your approach. Then we're going to go to C, and C is going to be code and explain what we code, and T is going to be tested. Okay. So first, let's go ahead and read the problem. So given a node in a connected unidirected graph, return a deep copy of the graph. Each node in the graph contains an integer value and a list of its neighbor. Okay. The graph is shown in the test cases as an adjacency list. An adjacency list is a mapping of nodes to list. Used represents a finite graph. Each list describes the set of neighbors of a node in the graph. For simplicity, nodes values are numbered 1 to n, where n is the total number of nodes in the graph. The index of each node within the adjacency list is the same as the node values. The input node would always be the first node in the graph and have 1 as the value. Okay, so let's go ahead and restate the question. So the task basically is to perform a deep copy of a given connected unidirected graph. So this kind of involves creating a new nodes object for every original node, and also to replicate all the connections, aka the edges between them. We're gonna have to ensure that the copy node links only to the other copy nodes. So we can link a copy nodes to a node nodes of the original graph. Okay. And our solution must handle these cycles right within the graph, and it must return knowns if known if the input node is none. So if we're not giving anything, we're gonna have to return none. All right. So here is the example. In this problem, the input is an ADG list. So you can set here you have it too, because for each node we're in the adjacency list, we're given the neighbor. So the neighbor of 1 is 2, the neighbor of 2 is 1 and 3, and the neighbor of 3 is 2. Okay, 1 is alone, so it has no neighbor. But I think that these examples are not super good to explain the problem. I will personally not say that in an interview, but since this is not an interview, I can say that basically all we have to do is to create a clone for the graph. So I feel like they're overcomplicating the problem a lot, because cloning a graph should not be that complicated. So with that being said, let's go to the point A, which is the approach. So on a high level plan, I will use a DFS or depth first search to traverse the original graph, and I'm gonna have to use a mapping, so a hash map, and a hash map will be used to store basically the original values that has been cloned already. And we're going to do that because by using depth first search, you want to prevent an infinite loop. And you want in this infinite loop, we will create an infinite amount of copies. So we want to ensure that only one copy is created for each original node. Okay. Another thing that I'm going to do in my approach is basically to handle the base case where the node that we're given is none. So if we're given a node none, I will return none. Okay. So with that being said, I think we're more than ready to jump into the code. So let's go ahead and code this. So first thing I will do is that I will create a hash map. So I will call this clone. And basically what's going to be inside the hash map is going to be the previous node and the clone node. So we know which original node has already been cloned. Okay, with that being said, we're going to create the depth first search function, and let me just call this clone. And we are going to be willing to pass a node into it. Okay. And the clone is going to go create a copy for each node in the original graph, and it's going to also use depth first search to to go add all the neighbors and ensure that we are creating the neighbors if they don't exist. And at the end, I usually create the function first and then the return statement, as I think they're the easiest parts to handle. So what I'm going to return is basically I called it clone, so it's going to be clone, and we're going to initially pass a node. So the node that we're given initially in the clone graph function. So this is what we're going to pass into the clone function. And we're going to do that. So we're going to return this if there is a node. Okay. Else I want to return none. So we already handles the edge case where we're not giving anything as a node. And now the first thing that we want to do, we know that clone is a depth first search function. So whenever we arrive at the top of the depth first search function, we want to see if we already have cloned this this function or this node. So we're gonna check if node is in clone. If it is in clone, we're simply gonna return its value. So we know that the clone node is going to be basically the value, and the node itself, or the original node, is going to be the key in our hash map. So this is the first thing we want to do. After this, we want to actually create a clone of the original node. So to avoid any confusion with the actual function, let me just call this copy. And the copy is basically going to be node. All right, and now we can see up here that in the node we can add a value, or we can add the neighbors. So let's go ahead and actually add the value. So let's say node.val. But at this point, it is possible that the neighbors of copy are not already are not already cloned, so we can't add them to the copy yet. And it's fine because we can see that in the node class, we're going to assert none as the default value if neighbors are not provided. So we're just going to have neighbors temporarily set to none. So this is fine. And once we copied it, we can add to our hash map the old node in the cloned node. So we're going to say clone at the key node, and this is going to be equal to copy. Okay, and now this is where we are going to use depth first search to append the neighbors and create the neighbors if they don't exist. So I'm going to say I will go through every single neighbors provided in the original node. So I will say for n in node dot neighbors. Okay, so for each neighbor's value, I will basically create a copy of them if they don't exist, and I will ask for this copy to the neighbor of our copy. So I will say copy dot neighbor, and I'm gonna append to this the copy function of the neighbor. So basically, when we first go into the code, we are gonna add the first node that the entry node, and we're gonna call clone. So we're gonna go here, and we'll ask if the current node is inside clone. Well, no, because we didn't add anything yet. So we are gonna create a copy of that node, and we're gonna add this original node or starting node inside the clone hash map. And it is possible that the node has a couple neighbors attached to it. So we're going to go for each of these neighbors. And for each of these neighbors, well, we are going to say that the neighbors of copy, which is the copy of the node that we have, we're going to say that his neighbors will be basically the neighbors of, well, the cloned neighbors of the original node. Okay, so see for each neighbors, we are gonna also use that depth first search call. So it's going to go back to the clone function, and if it exists, we're just going to return that function in it. And so we're going to add to the neighbors of the copy a clone version of the actual neighbors of that original node. And if they don't exist, well, we are going to create it, and we are going to also add the neighbors to this node itself. So it's quite a beautiful code to see it this way, and see it's that's everything we have to write. So let's test this out, and we add an error. So let's see why. So first, we are creating our hash map, right? Now we have our depth first search function that we called clone, and then we're checking if the node that we're passing is in the hash map, and if it is, we are gonna return it, so we avoid any double copy. And then we're going to create a copy, which is a node of the node's value, and then we're going to add in the clone hash map, the node, and we're going to set that its value to the copy. We're going to go for every single neighbors in the neighbors of the node, and of course after each recursive rounds of depth first search rounds, we have to return the copy. So otherwise we're never going to receive the copy that we created. So this is how we ensure that in our statement here at the end, where we return the function clone, this is where we ensure that we're going to basically give back a clone version of the entire node, and this is going to give us access to the entire graph. So let's set that again, and there you go. Awesome. So I still have to do the T, so that was basically the testing. We also have to speak about time complexity in that T, which is a testing and also reflective moment about your code, and you're gonna have to speak about your performances. So about a space complexity and the time complexity. For the time complexity, well, we're gonna have a time complexity of big O of v plus e, where v is the number of verticals and e is the number of edges. So we're gonna go basically linearly through all the edges and all the verticals or the nodes. So that's the reason we have this time complexity. And for the space complexity, we're just going through all the verticals, all the nodes. So we're gonna have a space complexity of big O of v. Okay, so I hope you learned from this video, and I hope to see you in the next one.